Landon,
Hey, good morning.
good morning. I've got some awesome stuff to show you today.
Yeah, I've been reading ahead a little bit this time, and I'm not surprised considering it's distributed loadings.
Yes. Let me share the screen and we'll get going. Distributed loads. So I've been hinting at this a little bit. Hello, Leah. For well, even when we did the truss project the other day, I actually showed you how to apply a distributed load to the roof, and now it's getting formal. So we're actually going clear back to chapter 4 and picking this concept up. So it's 4.9. And the point is, this is what distributed load looks like. You see the set of arrows up here. So distributed load is where you don't have just one individual arrow of force pointing at your truss or whatever, but you've got thousands of them. And so we've got to, well, do something we've done a little bit in the past, which is why this kind of goes back to chapter 4, which is turn all of that into just one load. So let me show you something kind of cool. So this is the house. Let's see, is there a date on here? Yeah. This is a house I designed. It's one of the burn houses actually that's in Phoenix for a customer. And so this wasn't that old. That's their last name. So this is like a month ago. So this is just one particular beam. And so let's see. It's a roof beam. I've been talking to you about that and how around here anyway, the dead load for the roof is 15 and the snow is 25. At least that's kind of an approximation for it. So roughly you're getting 40 pounds per square foot. Notice you're told that over here. 40 pounds per square foot that's sitting on this roof. And it has 23 feet of roof that's attributable to that beam. And so if I take 23 feet times that 40 feet right there, let's see, what is that? 23 times 40. I get 920 pounds. And notice that's what in the real language of the industry is the standard load of the roof. But then there's also it seems kind of weird, but they call it the self weight. In other words, the weight of the beam itself. Notice that's actually in pounds per lineal foot. And the particular beam that I chose for this, a 3.5 inch by 4.5 inch Versalam, which means 3.5 across the bottom and 14 inches tall. So the beam kind of looks like that. That particular beam weighs apparently 13 pounds per lineal foot. So there's a foot of it that weighs 13 pounds. There's another foot of it that weighs 13 pounds. That's what that's saying. So this is kind of what you're going to see today. Like you're not, I'm showing you something realistic here, but today you're going to see somebody put a load like that on it. And so you're going to see all these arrows up here. All you're going to see is just a beam. You're going to see a bunch of arrows, and they're going to say that is 933 pounds per foot that's on that beam. And notice that this beam is 16 foot forward to the edge of the wall right there. Roughly, that's a 4-inch wall, and this is a 4-inch wall. So overall, this beam is like 17 feet long. So does it make sense if I have 933 pounds on every single foot and it's 17 feet long? Notice the feet would cancel. 933 times 17. That's a total of 15,861 pounds that's on that beam. So if that beam is supported at each of those posts, does it make sense? This is simpler than a truss. We have the reaction then on that. Well, because this is uniform all the way across, does it make sense by just multiplying the pounds per foot times how many feet we have? That's going to give me the total, kind of the total load or the total weight or the total force on that beam. And so the reaction, since it's equal all the way across, I can just put half of it as far as reaction over here at beam 1 and beam 2. I can just cut that number in half. If I say divided by 2, I get roughly 7,930 pounds reaction at each of these sort of reaction over there. And over here, same thing, 7,930 pounds. Notice that's exactly what this says right here. Like that was all kind of calculated for me. Well, I say notice it says that's exactly true. Let's see if I add 3,025 for the dead load plus 4,864. I actually get 7,889. So it's only close, and that's because those two supports out there aren't actually 4 inches. They're a hair smaller than that. They're 3.5 inches. And so, but my point is, do you see the stuff we've been working on in action? And when I'm designing for a house, I'm picking a beam out like this. And these are some of the main numbers that I'm paying attention to that this off this sheet. Because remember down below, if I have this beam sitting here and there's a couple of posts on it, and these posts are actually pushing down into the ground, 7,930 pounds. What's going to happen on the ground if I set those in the dirt? We've talked about this before. But if those posts were sitting on the dirt and you had 7,930 pounds, what's going to happen to those posts?
You're going to sink into the ground?
Yeah. So I won't go into this calculation now, but effectively then what I'm doing is coming underneath it and designing a concrete footing that's big enough, like a snowshoe. I've mentioned this before, but like a snowshoe, I'm just designing a footing underneath the house that's big enough that when that weight is put on it, that concrete won't sink into the ground. So I'm putting a snowshoe underneath that post. That post is almost like a pencil, man. It's really sharpened because it's so small, it'll just poke right through anything. So unless I put something large on it, does the logic of that make sense? So what we've got to do with distributed loads like this, even though there's, thousands of arrows pointing down on top of this, and that's why I wanted to point this out, is notice that's exactly what you're seeing in this graphic here, is a whole bunch of arrows pointing down on this. That's kind of what we're talking about today. So let's see. So let's start with something a little bit more complicated. So let's look at a load that's a little more challenging than this. Let's look at a load that does this. So here's a beam being supported on a couple of posts, except for we're going to give this a different type of load. We're going to give this a triangular load. So what if it's not even all the way across? And to keep it kind of similar, let's say this beam is 12 feet long, and let's say this one over here is 984 pounds per foot. It's important to note that unit. You might think that should just be pounds. In other words, I have 984 pounds over there. But that's the pounds spread over an entire foot. Does that make sense? So it's not at a point. It's spread over an entire foot. Now, what's different about this, like last time I would have said, oh, great, 984 times 12. Now I know how many pounds are on that beam. But does it make sense, because this is a triangle, that there's actually 0 over here? There's no pounds at all. Now, as soon as you move 1 inch in, there's a little bit of pounds there, but right at the end, there's actually no pounds at all. So the problem is, and back in chapter 4, we really have to be able to do is the same thing we just did a minute ago. We've really got to reduce, we've got to reduce this to just one force. Like for our moment calculations, we can't have 500 arrows on the top of this. Does that make sense? We got to have one. We got to reduce this to 1 arrow. And we just did that a second ago. We took, let me just pull that back up for a second. We basically just replaced those million forces right there with one giant force right in the middle. It makes sense that it'd be in the middle of 15,861 pounds. And then we said, hey, because it's evenly spaced, then that would mean half is on one side and half is on the other. So it would be located right in the center. So we took the pounds per foot and multiplied by the feet, 17. And then we got 15,861, and we knew it was right in the middle. Well, we got to do the same thing now, but the problem is this is a triangular load, which is very different. So where would that be? And how much weight is that? So it's very different if it's a triangular load. And I think I'll erase this, but I was just giving a project in my calculus class. Those of you who had my calculus class, we did this exact project last year as an application for this. But if you have a retaining wall here and there's going to be a bunch of dirt on the backside, and then down here is just living space in a house or something like that, well, the dirt gets deeper and deeper and deeper as you go down. Therefore, that actually produces a triangular load. There's much more weight because there's much more dirt pushing down there. And as you get closer and closer to the surface, the dirt is shallower and therefore it doesn't push as much. So that's the kind of thing that actually produces a triangular load. Or you might have a house And the roof might look like this. So maybe here's the garage door. And so because you have a garage door, there's a beam over the top of the garage door. Well, does it make sense? There's not very much roof over here, but then there's more and more and more roof on it as you move across it. So that's the kind of thing that produces triangular loads. Now, fortunately, this isn't terrible because it's a triangle. Really, all I have to do to find the total force is really just kind of take the average. In other words, if I take 984 on one side plus 0 on the other, and by the way, we're going to have trapezoidal loads where the other side isn't 0. So that's kind of why it's good to think this way. So if I take those two and I divide by 2, isn't that going to be the average of those? So 984 divided by 2, I get 492. Does it make sense if you kind of made this into a uniformly distributed load, not a triangular load, that all of the arrows would be 492? So as an average, that's 492 pounds per foot. So then if I do the same thing, if I just say, okay, well then that's 492 pounds per foot times 112, I'm sorry, not 112, just 12 feet, and that's a fraction. The feet are going to cancel, so I end up with 12 times 492. That's 5,904 pounds. That's your total load. But does it make sense in this case because there's way more load on the right-hand side? You're not just going to be able to cut that in half and put half on one side and half on the other. And because there's way more on one side, does it make sense to you that it would probably be like right over here somewhere, maybe? It would have to be kind of over there, if you will. Does that logic make sense? The question is where? So here's one of the big problems we got to have with distributed loads, because we can't work with thousands of arrows. We got to reduce it to one. Well, we just reduced it to one. But the question is, how are we going to get it? How are we going to locate it? How are we going to know where it actually goes? That's the problem. So, trying to think about how I'm going to teach you this. How are we going to get, secondly, the location? Any thoughts on that?
Well, I guess we need to know the angle of a triangle, no?
Yeah, in a sense, you could figure out the angle of the triangle. Again, one of my gut reactions to this would be, if I came back here, does it make sense for that to be in the middle? Wouldn't I have to have kind of like the same area on that side as I had over on this side? If I could get those two areas to be the same, wouldn't that be where it would belong? Like, isn't that the middle in terms of kind of the area? That's kind of the idea.
Yeah, I would guess it might be just like kind of intuition, like 3/4 the way from the left side. But
I
don't
want
know
to
if
say
that's
2/3.
right.
Yeah.
Maybe 2/3.
Yeah, maybe 3/4 or
two-thirds.
2/3. I'd say those are both really good guesses. It kind of feels like it's right over there somewhere. Well, we know the total green area is 5,904. Does that make sense? That's the total area of the green shape. Because that's what we reduced all this to. So that's the area, in a sense, the area of the green shape. It's the total force. So that means, I guess, that this force, which I'll rehash as black, would be half of that. So this would be 2952. So I guess the question is where is that? In other words, if I said this is over a distance of X right there, is that 3/4? In other words, 9 feet, or maybe 2/3, as you said, maybe it's 8 feet. Where would that be? Well, one of the problems we've got is we got to figure out how much force is actually there. Remember that blue 55904 is like all of the green area all into one location. But if we look at the individual heights, so to speak, of these things, like this was only 984 right there. So the question is, what is that? If I kind of draw that in right there, what would that be? Well, we got to come up with an equation for that line. We got to come some kind of an equation. Would you agree it has a rise of 984 and a run of 12? So the equation, if I think of this as kind of the XY axis right here, I don't know, let's see, do I want to say force? Well, let's say W. This is what it's for weight, if you will. This is the weight at X equals 12 feet. That was the weight in pounds per foot. So it's kind of a lowercase w. Well, wouldn't the weight be equal to the slope, which is 984 over 12 times X? Got a bit of an unstable internet. It's like my notes are showing up behind what I'm saying. So it'll pop up in a second, I guess, but I wrote W equals 984 over 12X. Notice that actually works. In other words, if X is a distance of 12, in other words, if you're at location X equals 12, does it make sense you actually get the right answer, 984? And if X is 0, you end up with 0. Do you see how that's working? So in other words, how much weight you're at depends on where you are. So the X is where are you? And the 984 over 12 is kind of like the slope. Now, fortunately, because I made this up a little carefully, 984 divided by 12 comes out 82. Looks like mu, not W. 82x. So then if any place I'm at on here is 82x, then don't I need, well, didn't we just find the area a minute ago? We took 984 times 12 and divided by 2. So now I need that kind of black area. I need that area, which would be 82 times x, because that's the height of this arrow right here, this black arrow. That's how tall that arrow is. Again, we don't know where that is, times a distance of x divided by 2. Isn't that the same thing we just did a second ago? It's identical to that. I should say to that whole process, because then we multiplied it by 12. So it was 984 times 12 divided by 2. That's how we got 5904. So we need 82 times x again divided by 2 to give us that half weight, 2952. What am I doing wrong? I'm actually doing something wrong here. Thought I was simplifying this for us a little bit, but I'm thinking I'm Hi guys. Runs over the run and 12. Mhm. Sorry, I was trying to simplify this because I was thinking you could do this without an integral. Now I'm looking at it because this isn't working. This isn't giving me the x. It turns out the right answer to this is the location of this is 2/3. One of you had your intuition right on this. In other words, that x really is 8 feet, which is 2/3 of whatever L is. But when I'm solving this equation that we just created down here, I'm not getting 8 like I should. So I'm thinking, I was trying to simplify it because last time I did this, I did it with integrals, and I don't know, it was in my mind as I'm just reasoning through it with you out loud that we didn't really need to do this with an integral, but it's kind of looking like we do. Either that or I'm making just an algebra mistake someplace. I just can't, if I am, I'm not seeing what it is.
So Did you get 8.4485 when you did it?
Right. And it's actually supposed to be 8.
Yeah.
I was just thinking logically, both of the two areas, but I'm sort of teaching this different than I did last time, just because I'm thinking I understand it better, but now I'm thinking maybe I don't. I'm thinking these two areas would have to be identical to put that exactly in the middle. But I'm just troubled. It's like, why wouldn't this work? So let me write this down. So this would kind of imply, this would imply that X is as, so I'm going to multiply by 2, divide by 82, take the square root. X is 8.485. But that's not true. Because my point is I don't think I need an integral to find this area because it's just a triangle. I will need an integral later on. We'll talk about that. But right now, I don't think I do. So I'm just, that should have came out 8 is what I'm saying, and it didn't. So is there an algebra mistake someplace? Did I punch a button wrong anywhere along this process? I'm just going to punch buttons for a second here. 984 times 12 equals divided by, no, that's 5904. Didn't make any mistakes there. Cut that number in half. 2952. I don't see anything wrong with that. This is utterly dumb. I apologize, team. There's something really stupid wrong here, and I can't seem to figure out what it is.
I wonder if it maybe has something to do with it being like in pounds per foot and not actually in pounds. Well, no, that would, I guess that is in pounds, not a 50904.
Hmm.
I think I'm wrong. I think it has to be an integral instead of just area, but I guess I can't figure out why that is. Well, to progress for a second, I apologize, for a triangular load, the location is 2/3 of the way in. And I guess I should say from the short side. From the low side. So in our case, 2/3 of 12 is 8. So it should be 8 feet in. So that's its location, 8 feet in. I think my logical something wrong with my logical concept, but I can't see why. But I think it's not true that those two areas are the same area. That sure seems like they are, and that's what's bothering me. But so if that's true, to progress, then we found our 5,904 pounds because that's how much weight is there, and its location is 8 feet in. So let's just kind of redraw that really quick. So there used to be hundreds of loads, and not only that, they were all different sizes. And so that's very terrifying, but we've now located it to be right there, 8 feet in from this side, 2/3 of the way in. Now, what's really cool about this, does this make sense? We can come back now and figure out we could find the reactions at the 2 points on the end. In other words, if this is point A over here and this is point B, does it make sense we could find the reactions of those 2 points, which you would need to do? Now, as far as, and we'll get to an assignment question in just a second, but just so you're kind of getting prepped for that. But that 5,904, 8 feet in, like that's most of your questions in your assignment is you're done. There you go. You found it. You're done. But just to go on and find the reactions, let's do that now. As we said, this certainly B is going to have more of the weight. So let's find the reaction at B. So I could find the reaction at B by, I hope you understand, by summing the moments at A. So what we really have down here, switch colors, is I'll call that force at A and force at B, thanks to the posts. So the sum of the moments at A needs to be 0. So what would the sum of the moments at A be? Well, don't I have the force of B pushing up a distance of 12 feet from A? And then don't I have 5,904, a distance of 8 feet from A? And all of that has got to add to 0. now that I've reduced that triangular load to one single load at one location. So that's easy to solve. If I take 5904 times 8 and move it to the other side and then divide by 12, I get 3936. The force at B is 3,936 pounds. That's the reaction at B. Does it make sense if I wanted to get A, now that I know that one, I could just do the sum of the forces in Y to save myself a little trouble? Because obviously it would be true that with 3,936 pushing up and 5,904 pushing down, that the force of A better push up to balance that. Again, yeah, you can get this one by logic. Clearly, 5,904 minus 3,936. So that means the force of A would be 1968. So that makes sense. So are those, is that 1/3 and 2/3? Do you think? Is 3936 also 2/3 of 5,904? Notice it is. Okay, let's take a stab at just kind of a book related question and see if we understand it now. Import, where am I? I don't want to be here. I want to be here. So here's a question that's like the questions that are in your book. Let's see if we can figure this out. So notice this is not a triangular load. It's well, I guess you'd call that a trapezoidal load. Notice they don't ask us to find the reactions at A and B. That's actually next. That's what's going to happen in the next section. You already know how to do that. But all they're saying is replace that loading by an equivalent resultant force, and where is that thing? So the problem is, how do you handle it when it's a trapezoid? Well, the easy.
Well, we could just
Go ahead, Landon.
split into a triangle and then a rectangle.
That's exactly right. That's the easiest way to handle this. Your intuition is right on the money. So if I split that up, then don't I have kind of 2 going all the way across the bottom and 3, since it's 5, like this is essentially 3 now from here to there. So the rectangular portion of it, if I take 2 kilonewtons per meter times the fact that that load goes all the way across, which is 6 meters, times 6 meters, then that gives me, the meters cancel, I end up with 12 kilonewtons of load. So where's that located?
Right down the middle.
Yeah, right down the middle. Easy. So I know that's in the center. At the center. I guess you could say that's at 3 meters then if you wanted to, but whatever. Then you also have the triangular load. So the triangular load is 3 kilonewtons per meter times the overall distance of 6 meters. But times a half because it's a triangle. So you end up with 9 kilonewtons for that. And that would be at 2/3. And I'll say here more particularly from the left, since that's where 0 is. Notice they were nice about that because 2/3 of the way in would be 4 meters. That's right on top of B, in other words. So let's draw those in. So I've got this one right here. That's 9 kilonewtons. And then I've got this one right over here. That looks centered right in there. That is 812 kilonewtons. But I haven't done it. I don't have it.
Medford Truss.
Medford Truss. But I still haven't reduced that to one individual load yet. How did we do that before, back in chapter 4? How do I get that to be just one? And how do I figure out where that is?
We could just take the moment around to A, right?
Yeah, take a moment.
The
That's
sum of
what
the moments around A, rather.
So we have a total of 21 now. Does it make sense? We know we have 21. We just don't know where it is. It seems like it would be somewhere in the middle of the two. Do you agree with that? So if I come back here, I clearly know that I've got 21 kilonewtons is actually the final answer. I do have the resultant force now, 21, but I just don't have its location. And yeah, didn't we do that based on moments? So location. Well, if I did the sum of the moments around A, actually I'm going to do this with colors. Now let's do it this way. The sum of the moments around A. Well, I've got let's actually just consider it as the moments around A. I'm just going to do this based on logic. If I look just at the moments around A, would you agree that if I think of the moments in terms of what kind of orange it is, if I say, well, I know I have -12 times the distance of 3, since that was 3 meters in. And then I also have 9, which is also, if I'm going around A, if I choose to go around A anyway, I have -9 times its distance, which is 4. Wouldn't that have to be equal to -21 times, well, whatever X is? Does that logic make sense? Will those have to be the same thing? So let's see, I get negative 36 and negative 36, which is negative 72. So if I divide both sides by 21, 72 divided by 21, I get a distance of 3.43. X is approximately 3.43 meters. There. Now, we effectively just did that entirely based on, well, I don't know, maybe I'll just say logic. Let's try to do this a second way now, entirely based on calculus. And I'll show you why calculus is important before we dive into it. I don't know if we'll have time to get to this question today, but take a look at. This is another example. Maybe we'll end up getting into this the next time we get together, but notice that load is not even straight lines. So, you know, maybe that's a cable. And so I'm getting kind of a curved load associated with it. And so I'm not just going to be able to break it up into shapes that I understand always. So we're going to have to do this problem with calculus. But let's see if we can get the same answer for the one we were just working on using calculus. So let's see, can I? So the question is, and this is effectively kind of what was wrong with my previous answer a second ago, and I'll kind of sort that out and we'll talk about it tomorrow after I kind of get my mind around why that didn't work. But let's think about this. Would you agree the slope of our line up there is a rise of 3 kilonewtons per meter and a run of 6 meters? So our slope is 1/2. So that means kind of our, oops. That means our weight is just 1/2 x. Now let's just play with that for a second. So if I come back up here, that means if I stuck in an x of, well, watch this because our equation's still not quite right yet. If I stick in an x of 6, a total distance of 6, then I'm supposed to get 5 kilonewtons for my force up there. Do I? No. If I stick 6 in and I take half of that, I only get 3. In other words, I'm getting 3 right there. Well, that's because everything was raised up 2. Does that make sense? So my equation is actually 1/2 x plus 2. Sorry, it looks like my screen again is lagging behind. That's actually my equation because this is not just a triangular load, it's a trapezoidal load. Again, think about that line. It's actually starting at 2. So does it make sense if you stick in now an x value of 0, 1/2 times 0 is 0 plus 2. Oh, look, it worked. If I stick in an x value of 6, 6 times 1/2 is 3, 3 plus 2 is 5. Do you see how it's working? Like that's the actual equation that tells me what my force is no matter where I am. Do you understand the logic of that? We need kind of that force. We need that equation that produces W. And it should be noted that that W is still kilonewtons per meter. Now, if you stare at this a second ago, did we not do this? Watch this carefully. A second ago, didn't we take the forces up here times the distances? So there's a couple calculations we can make now. Watch this with respect to integrals. I want you to see if you can figure out what this calculates. So if I take that equation right there, 1/2 x plus 2 dx, think about what the dx is doing. And since our beam was 6 meters long, then I go from 6 to 0. I want you to notice what the answer to this is and what this means as a result of that. Let's see. So the integral would be the integral of 1/2 x would be x squared divided by 2. So that'd be 1/4 x squared. And the integral of 2 would be 2x. And then I'm going to evaluate that at 6 and evaluate that at 0. If I do that, I get 21. What was 21 a second ago? And why did that produce that?
That was the total force that the beam all the forces exerted on the beam.
Yeah, that's exactly right. That actually was our total force. But let's think about why that worked the way that did. Like, why did an integral do that for us? Well, if the W value was effectively this height right here for a given x, then don't I have, like, the only time that force is what it is right there at that spot, right there at that location. So isn't its sort of thickness, if you will, a little bit of x? So didn't the y coordinate, or I guess I should say the w coordinate, since of the equation, the w was kind of the height of the arrow, and the dx was a little bit of thickness. And so what I really did is I added all those little areas together. And isn't that what we just did a second ago with Landon's good ideas? Didn't we find the area? Didn't we find the area of the rectangle and the triangle and add them together? And isn't that what integrals do, is find areas? So it sort of makes sense that that'd produce the same answer. Can you see that's going to be important if the shape is a curve or something? So we found those, but then down below to locate it, didn't we take those areas and multiply by distances? So I secondly want you to watch what this calculates. If I take that same exact idea from 6 to 0, except for I take 1/2 x plus 2, but I actually also multiply it by x first, isn't that a force times a distance? So this was actually just the sum of the forces, which was an area, whereas the bottom one is actually the sum of the moments because it's a force times a distance. So let's see what that produces. So let's see, that would be from 6 to 0. If I distribute x in there, that'd be 1/2 x squared plus 2x. And now if I take the integral of that, 1/2 x squared, the x squared would turn into x cubed. And I would divide by 3. Well, there's already a 2 down there, so it'd be a 6. And then the integral of 2x would be x squared. And when I divide by 2, the 2's cancel. So now I evaluate that at 6 and at 0. Let's see, what do I get when I evaluate that at 6 and at 0? I get 72. Kilonewtons. Or kilonewton meters, don't I? Because force was kilonewtons and x was meters. And keep in mind that don't forget dx is also in meters. So what you really have here as far as units go is this was kilonewtons per meter, and this is meters. And so when I multiply those, that's why I get kilonewtons. This one down here, this is kilonewtons per meter. I'm multiplying by meters and by meters again. So these meters cancel and I get kilonewton meters, which is, that's the unit for moment. So what I'm actually getting here is the total moment created by all of those forces put together. And isn't that the same thing we got right here? That was 72. So again, we were able to do this without calculus because it was a rectangle and a triangle. So in the end, to get the location, so I got my 21, which is the force. What's the location? The location is at 72 divided by 21. Notice that's kilonewton meters divided by meters. So the meters, I'm sorry, kilonewtons on the bottom. Kilonewton meters divided by kilonewtons. So when I divide those, 72 divided by 21, that's what we just did mathematically a minute ago. You end up with 3.43. And the kilonewtons cancel and you get meters. That's your distance. So I guess, kind of walking out the door, you could say that the integral of the W times dx, that's going to give you the total force. So in our last example, that gave us the 21 kilonewtons. Newton is force. And it's important to understand that that weight is, like in our system, is not just pounds, it's pounds per foot. It's like a rate. It's the rate of weight, if you will. It's the slope. It's the equation that tells you what the forces are if they're not all the same. If you take the weight times x dx, then you're getting the total moment. And then if you divide those, you're getting the location. So let's take, with the last little bit of our time, let's take the calculus approach and sort of build that 2/3 thing that I was just sort of asking you to believe and that something wasn't working for, like I was screwing up. So let's take a look at this triangular load. And since it's triangular, that means its equation is equal to its slope. So let's give this a name. So I'm going to call this capital W for weight. So we'll say this is in pounds per foot. If we take that pounds per foot, and this is our length, what we did to find the slope a minute ago is we took W divided by L. Do you agree with that? And then if you multiply it by X, wherever you happen to be. So that's the equation that tells you kind of how strong the force is at a given location. So calculus says, let's find the force. So what I called it a second ago, the total force. We said if you go all the way to the end, which would be from L to 0, because that's how long this beam is, and you just take the equation W over LX and integrate it with respect to X. Remember, W and L are constants. So let me make a note of that. W and L are constants that would be given as a part of the problem. Then isn't that integral? Well, doesn't the X grow in X squared and then you divide by 2? So X squared, I divide by 2, and then I evaluate that at L and I evaluate that at 0. So if I put in L for X here, don't I have L squared over L? So I have WL squared over 2L. So those L's cancel and you get WL over 2. Isn't that what we just said a second ago? When that was like 984, didn't we go 984 times 12 divided by 2? Like, doesn't that make sense? That the area, because it's a triangle, the area would just be, well, the height of one side, which is W, the height of this side, which is W, and the length over here, multiply those together and divide by 2. Like, we don't really need calculus to find this, right? Now let's find the total moment. We said that was also from L to 0, except for we're taking W, capital W, over L times X, and we're multiplying it by X again. So now it's a force times the distance. It's kind of cool to see calculus in action. So then there's still a W over L. The X squared grows to X cubed. And then I divide by 3. And I evaluate that from L to 0. So don't I end up with WL cubed over 3L? And the L's cancel, and I end up with WL squared over 3. So what's the location? It's time to switch colors. What's the location then? Well, I take the moments divided by the forces, which would be the same as WL squared over 3 times the reciprocal, 2 over WL. What happens to that? W cancels with W, one of the L's cancels with one of the L's, and you end up with 2/3 L. Where is it located? 2/3 of the way over. So for a triangle, that's something you could memorize. I'll show you this in your book because it's in there somewhere. I think it's at the back. It's either at the back or the front, but I'll just hold it up. I think it's at the front. I swore this was like right on the cover or something. I don't know where it is. I don't want to waste any more time. There's a page that kind of shows where some of these are. We'll get to that later, I guess. But so that's why I knew in that original problem that 12, 2/3 of the way over was 8 feet. I still can't figure out like what I was doing wrong. In a sense, we just did this, proved it using calculus, and I was just trying to do it using kind of the area, the idea that Landon came up with. Just do it based on the areas, and yet I wasn't getting the same answer. And it's like, I don't know what I'm doing. I don't know what I was doing wrong there, but. How's your brain? Is your brain in pain? Let me show you something kind of cool, just real quick, because I have it. So notice the arrows that are on top of that beam up there. So this has got a triangular load on it. But it's also got the self weight of the beam on it. So if you notice down here, kind of like what I showed you before, it's got 14 pounds per foot, which is the weight of the beam, which is and notice that's considered to be the tag. It says 0. That's the 0 load. Do you see how that's just a bunch of rectangular arrows running down the length of the beam? So that's 14 pounds a foot. But then you have load number 2, or sort of load number 1, 0 and 1, trapezoidal load, pounds per foot. But then notice right here, that's a total of 1,500 pounds. So in a sense, then what you have down here is kind of like an arrow that's 1,500 plus the 14, so 1,514. You'd have 1,514 pounds on that side of the beam. And then down on this side, you don't have any of the 1,500. You only have 14 down there. Notice it's doing some math for me automatically here. Do you notice at bearing 1 right here, I'm being told the reactions right there. If I add those up, 2666 plus 1907, that's 4573. So that's how much of that weight is on that side. Whereas if I go down to bearing 2, I get a much larger answer, 5434 plus 3752. That's a total of 9186. So do you see how that's so incredibly important? And also the other thing I want to show you is, do you notice that's all entirely built in? In other words, I didn't do any of that math, the computer did it. But what we're talking about here is the math that the computer is producing. In a sense, you should be able to arrive at those numbers yourself. And again, your ability to arrive at those numbers is going to be based on, can you replace all of those thousands of loads with just one big load over there, given that it's both a rectangle and a triangle, or just using our calculus technique? So just for the fun of it, our W equation here would be 1500x, because that's the rise of this line, of that slanted line up there. Since it started at 14 and then went to 1514, it's rising 1500, but then it's doing that over a distance of 18 feet. So it's W over L. And then, because it's a trapezoid, it would be plus 14. That would be our equation for that top line, this sort of top angled line up here. That's our weight equation. And notice in this case it's pounds, so that would be pounds per foot. If you put 18 into that equation, you'll get 1514, because we know the answer over there. If you put 0 for x, x is the distance. X is the distance into wherever you happen to be interested in. If you put in x is 0 into that equation, you get 14. Those are the two that we know. That equation's working. Since we have a minute, let's go ahead and calc this. Total force would be the integral from 18 to 0 of our equation. Let's see, is 1500 divided by 18 happen to be a whole number? No, so I'm going to leave it alone. 1500 over 18x plus 14 dx. That's going to be the total load that's on that truss. So that would be 1500x squared over 2 times 18 plus 14 times x, and I can evaluate that at 18 and at 0. Unfortunately, when I put 0 in, it's just 0. So if I say 1500 times 18 squared divided by 36 plus 14 times 18, I get 13,752 pounds. Which is all of those added together. Now that's not exactly the same, and I actually have talked to people about this. Those are off by 7 pounds and actually don't know why. I think it's rounding. I think it's just rounding is the reason. So that's kind of cool. We know how much weight is there, but again, that's cool to know that, because that's part of, you know, what size beam do you choose? But the second part of it is we got to know where it's located so that we know how much of that weight to put over at bearing 1 and how much to put at bearing 2. Do you see the larger picture here? So let's get the total moment. By the way, notice the right answer to the total moment is right there. 30,111. Let's see if we get an answer that's close to that, because we know how to do this by hand. Total moment. I'll do this quickly because I know I'm taking too long here. So that'd be still from 18 to 0. It would be 1,500 over 18 x plus 14, all multiplied by x before you even take the integral. So that means this would be an x squared and this would be an x. And now take the integral. So that'd be 1,500 over x cubed, and 18 times 3 is 54. And this would be 14x squared over 2, which would actually be 7. But I'll go ahead and write it like that. Oops. And now I can evaluate that at 18 and at 0. Let's see what I get when I put 18 in there. 1,500 times 18 raised to the 3rd. Divided by 54 plus 14. I got 100. 15 times 18 cubed divided by 54 plus 7x squared. That's right. I got 164 to 68. That would be foot-pounds. And again, I highlighted 30,000 and I'm thinking, uh-oh, those aren't the same. I wonder what's going on. I actually don't know the answer to that right off the top of my head. Those must be referring to two different things. I was actually thinking we'd get the same answer to this. If I divide these two, I get 11.945 feet. Now this wasn't a triangle. I need to shut up here, but this wasn't a triangle, so it isn't exactly 2/3, but isn't 2/3 of 18 12 feet? And so notice this is really close to being a triangular load. Do you understand that? Because one side is 1,514, the other side's only 14. That's a really tiny number. This is really close to being a triangular load. Therefore, it's really close to 2/3 of the way over. So I'll shut up with this. So then I could come over here and say this is 11.9 feet or whatever that number was I just had. And then we figured out it was 13,752 pounds. Does it make sense? Armed with those two numbers, you would be able to determine the reactions, which is actually what we're going to do in the next chapter. You already know that. But we'd be able to determine the reactions at each one, which again, for me, designing this is extremely important, because that's where I've got to go put footings underneath them. And so I'm going to need a way bigger footing on the right side than I'm on the left. I get all this stuff for free. I just punch this in. I don't have the complete answer to this, but as to why this number is 164, does it make sense? That might be because that's the total moment of the entire beam rotating around bearing 1, like as though the other bearing doesn't exist. Whereas when a beam breaks, it's really only to the middle. It's only from 0 to 9 feet where it breaks in the middle. That's the actual moment that's created in the beam itself. I think that could be the answer. I'm actually not sure. I gotta think about that. Okay, your brains are probably full. So what I want to do, let's see, what is today? What I want to do next time is just kind of play around with that some more. We got a little bit more time, but we'll do a couple other examples. I'll talk about kind of what creates other things that create kind of triangular loads, and we'll look at that curved example and kind of play around with that some more. So stay and ask questions or go out in the sunshine.
Sounds good. Bye, Doug.
See you later.
See you, Doug.
See you, Landon.